Hello everyone. We will be starting this session in 5 minutes as so that some more students can join the class. So, just wait for 5 minutes, then we will be starting this live session. We'll be starting this session now. So, let me first introduce myself. My name is Himanshi Singh. I'm currently a PhD scholar at the Department of Mathematics, IIT Jodhpur. And I'm pursuing my PhD in a broad area of probability and statistics. And also, I'm TA in this course, Essentials of Data Science with our software tool, Sampling Theory and Linear Regression Analysis, which is now this course is taught by Professor Shalab, and all the videos and the content of this course is getting uploaded on the SWAM portal every week. Okay, and I'm here taking a live session every week so that we can discuss some of the practice examples and we can recap all the things which has been already discussed in the previous week. So this is our sixth live session. Okay, and we conduct this live session on every Monday from 6 to 8 p.m. And this is our sixth live session, and this is the live session schedule for all 12 lectures or live sessions. Yeah. Apart from this schedule, we have these are the important links. So the first one is the Google Meet link from which you can join this meeting, which is a live meeting. Okay, and apart from that, I am uploading all the recordings of these videos on YouTube on my channel, which you can access by using this link. Okay, apart from this, all the PowerPoint presentations and the R script which I'm discussing during this live session, all of those documents are uploaded to Google Drive, for which the link is given here in the third number. So you can access all those documents from there. The recap, the summary, and the R scripts. Okay. Okay, so our plan for live session, generally it happens that first I give a brief recap about the topics. Then if there is something, then I'll just demonstrate those things in R. And then we will be doing practice examples. And if someone in the class have some doubt, then we will discuss that also. Okay, so I hope that these things are clear. I'm continuously repeating all those things in the starting of this live sessions, because so that like you people are aware of all those things. And if someone who is firstly watching this lecture only, then he or she can get the idea about the things. Okay, so I hope this is clear. Then we will start the uh, today's live session. So in the previous live session, we were discussing um, about the sample proportion. Like if, for example, I have a qualitative data such that it can be divided into two disjoint classes. Okay, so if it happens, then how to make that data into quantitative data in order to perform some statistics on it, because we want numeric values, numeric quantities in data in order to perform statistic or in order to use the statistical tools. So basically, this indicator kind of a function was defined, so that if there are two classes in which the population can be divided, then the elements which belongs to class C are we are assigning 1 to those elements, and 0 to those elements which are in the other class. For example, C and C star. On the basis of that, if I construct a vector y1, y2 till yn, then the population proportion of class C will be y bar, which is basically we can find out it by using the population mean thing, and the sample proportion is the sample mean y small y bar, which is basically you sum all the entries in the sample and just divide it by the length of the sample. So this as will be the sample proportion. Apart from that, we have the expressions for capital S square and small s square in the form of capital P and capital Q and small p and small q. So basically here the q is 1 minus p, nothing else. So here this is, so we know that capital S square is nothing but 1 upon n minus 1 summation yi, or I can say yi minus y bar whole square. Okay, where I is going from 1 to capital N. But in the form of PQ, we can write it like this: capital N upon n minus 1 into PQ. By doing some of the algebra, we can find out that it is in the form of PQ, it can be written like this. Both of them are same if we are considering yi to be this one, which is defined like this. Okay, now this is the sample proportion. So this is basically an unbiased estimator for the population proportion. Okay, we can also say this by, because we know that small y bar is a unbiased estimator of capital YR. So small p is unbiased estimator of capital P. Now, if we have this unbiased estimator, so then we have to know that what is the variance of this estimator. So this not so variance of this P under the without replacement technique, the variances. So this was, we defined it earlier. Now in place of s square in the form of PQ, we can write it like this. We just replaced s square by this quantity and we got this. And similarly, under with the replacement technique, the variance is this, and we can like replace this. So basically, variance of P under this with replacement, it is this. But if we change this s square into n upon n minus 1 PQ, then we just basically got this PQ by n. Okay, now unbiased estimators for these two quantities are given by these expressions. So which is capital N minus n upon n into n minus n PQ in the form of small p and small q, and this is PQ by n. And also, if you are if you are doing all these things in R, then in place of there is not always necessary to write in the form of PQ. It is just the way to write it. Okay, you can also directly write in the form of s square and just calculate the capital S square, small s square, whatever is provided to you, and just find out the variance, the estimators. Okay, and this is only the representation in the form of PQ. Like how can we represent it in the form of small PQ? And this standard error is obviously we take the square error of these estimators, then we can find out the standard error. Okay, so this was about the how to find out the mean and variance, mean of how to find out the population, the sample proportion, and what is the estimator of it, and what is the variance of that estimator. Okay, now apart from this, we will now talk about the confidence interval. So the confidence interval for this is, so for this population proportion, which is capital P, the 100 into 1 minus alpha percent confidence interval is given by this. So this is true when I am considering capital N and small n are large, so that the distribution can be approximated by the standard normal distribution. Then we can have this confidence interval P minus Z alpha by 2 square root of variance of P, comma P plus Z alpha by 2 square root of variance of P. And here we can use the estimators whenever if we need it, then we can use the estimators also here. And this n by 2 is the continuity correction. So since this yi, the random variable which we are considering, so this yi is a discrete random variable. Okay, so in place of, so we are basically so this capital P is 1 upon n summation I going from 1 to n yi. So this is the capital P, which is the population proportion. Now this is a discrete random variable. Now, since this is a discrete random variable, but we are approximating this random variable by a standard normal random variable. So basically, we are saying that P, capital P minus a small p, so which is basically, if I take this expected, so this is basically the sorry, not this. So P, small p minus capital P divided by what I can say, a square root of variance of P. Now this confidence interval is coming because we are saying that this is standard normal 0 comma 1. So we are basically, what we are doing, that this small p, or I can say the capital P or the small p. So if I say the small p is 1 upon this sample version, so I going from 1 to n. So this is a discrete random variable. Because why? Because it can take value like that. Support how this random variable is discrete. Okay, we are getting numbers, or this is not a continuous random variable, and we are approximating it by a standard normal random variable, so which is basically corresponds to a continuous distribution. So because of that, we sometimes use this continuity correction. Okay, however, sometimes we can use, sometimes we cannot use. So it totally depends that whether what is the requirement of the question. Okay, so this is this quantity is, that's why I didn't subtracted here. Now, so this is basically the confidence interval for the estimation of population proportion, or the confidence interval for the population proportion. Okay, in the previous lectures, we have already discussed that Z alpha by 2 is nothing but the upper alpha by 2% points of normal mu comma sigma square. So if this is normal mu comma sigma square and this is Z alpha by 2, so this basically this area is alpha by 2. Okay, that is probability z greater than equals to z alpha by 2 is alpha by 2. So this basically means that this is that point. Also, small s square can be calculated by this command. So small s square we basically use so many times whenever we are using this capital S square, and the estimator of this consists of small s square, and we are basically finding out the estimates by using small s square. So that can be calculated by this command variance of y. And also z alpha by 2. So here this z alpha by 2 we can find out using the normal tables. And apart from that, if I want to find it in R, then I can just use this command q norm 1 minus alpha by 2. So this will be z alpha by 2. Okay, so this command will give me z alpha by 2. Okay, so now we know all these quantities and we can just put those quantities here and find out the confidence interval. Okay, now if I'm in R and if I want to code all the things, okay, so if I have a qualitative, so I have a sample, for example, y, if I have a sample and here it consists of some qualitative data. Okay, so then I have to first make that data quantitative, okay, in order to further move towards the statistics. So for that, what I can do, I can construct another data vector. Okay, so where I just give a condition. So for example, this data vector is consists of two classes. So elements from two classes is coming. So whether, for example, I have the class which is, so if yes and no, two classes we can classify into this yes and no. So some set of people is saying yes for a particular question. Some set of people is saying no for a certain question. So this way the data is collected, and I have this sample which consists of these entries yes and no. Okay, so basically that is a qualitative data, and I want to make it quantitative. So what I will do, so for example, this is a y, so I will just say that I will, if I write y star to be y is equals to yes. Okay, so then what will happen that this y star will be now a logical vector which will give me the answer in true false. So wherever there is yes, it will give me true and true in y, and wherever it is no, it will give me false. So it will be kind of this vector. Okay, and according to the entries in y. Now I want to make it a quantitative. So I'll just use the command s dot numeric y star. Then that will give me 0 in the places of false, and it will give me 1 in places of true. So now this construction is done. Okay, so where yi is 1 and yi is 0. So if 1, if it is in C, and if it is in C star, so this C and C star will be taken care of by yourself. So whatever is asking the question, according to that you will make your C and C star. Okay, accordingly only you have to make this condition, so that if you want 1 on those places where there is yes, and you will make this, and if you want 0 in place of yes, and you want 1 in place of no, then you have to write it y is equals to no. Then if by using s dot numeric you will get 1 at those places where there is no. Okay, so this way, this now quantitative data is done. Now we have converted the qualitative data into quantitative data. Now further, if I want to, so for example, this we have done for the whole population, and I want to take a sample from that population. Then I'll just, this vector, I'll just write this sample yq size is equals to n. I want a sample of size small n. And I'll write replace is equals to true if I want with replacement. Replace is equals to false if I want without replacement. So this we have studied before only. Further, I want to estimate the population proportion. So if I want to do the population, I want to, so for example, I have drawn a sample ys from this, and I want to now find out the population estimate of population proportion. Then I'll just find out the y bar basically. So that is found out by using this command mean of ys. And further, if I want to find out the variance of sample proportion, so we have two different formulas for that already with us. So which is basically n minus n upon n into n minus 1 pq, small pq, or we can also write as capital N minus n upon capital N n into small s square for without replacement. And here we have small s square by n. Okay, so by those commands we can just find out, we can just give these commands and find out the variance of the sample proportion. Okay, so this is the way by which we can just take the qualitative data, make it quantitative, and do the statistics, which we have done before also. Okay. Now, so this was about the sampling for proportions. Okay, so whenever we are we want to find out the about the proportion, that how much of the proportion is with a certain class, and what is the proportion of another class. Okay, now further, so now till now we were only doing the simple random sampling with replacement or without replacement. So basically we would discuss, we before in the first or second class we were discussing that there are two kind of sampling: random sampling and non-random sampling, and we are majorly interested in random sampling because of its probabilistic base. Okay, now in random sampling we already discussed about the simple random sampling. Okay, which have two parts, that is simple random sampling with replacement and without replacement. Okay, so now simple random sampling is majorly useful when the whole population is homogeneous. Okay, it is not like there are certain groups, so there is no heterogeneity, there is very homogeneity in the population. So that's why simple random sampling was used, because we were considering each outcome to be equally likely under the assumptions, and the distributions of each of the random variable, or I'm taking the sample, so the distributions were identical, they were not different. Okay, so however, if this is not the case, if the population is heterogeneous, for example, so there is a lot of variability in the population. So for example, if I have so for example, there are there is a population of different countries. Okay, for example, I have many countries, and this is the population of the for example, 5 countries I have taken, and those 5 countries are the, I'm considering them to be the whole population. I want to analyze something on this population. Okay, now if I want heights of the people, so there may be a case that due to some of the geographical reasons, some people, all the people, so there is a difference in heights of these people. So for example, in this country, in this country A, the heights of the people are less, and in country B, the heights of the people are comparatively very high. Okay, so then what we can do, we can just make groups. So country-wise groups we can make, or not even the height. We can also take different things. So for example, if there is a country where always the weather is extremely hot, and there is a country where weather is always extremely cold, so then we cannot do the sampling directly. We have to just first make the groups, and then we have to do the sampling and find out the, because the population is heterogeneous. Okay, there is a so if I have these 5 groups and I'm taking it as a whole population, then there is very much heterogeneity between these two groups, and they are not familiar, there is high variance. However, there is low variance in between, in among there is high variance between this, okay, between these two, any of these two, but the variance is very low if I consider only this group, or only this group, or this group, or this group, or this group. In that kind of scenarios, we use this stratified random sampling. Okay, so populations can be heterogeneous in many other ways, but here the assumption is that it is heterogeneous. If this is a population, and if I have to divide it into different groups, so within the groups it is homogeneous, but if I consider between two groups, then it is heterogeneous. Okay, so in this way, this stratified random sampling has the base or the motivation to be defined. So further, I'll just give you a little bit of procedure about the stratified random sampling. So how, if I have such kind of population, then how to do sampling from it. Okay, so if I have a population of capital N units, okay, then so if I have a population of capital N units, then we basically divide it into, for example, K groups, and each group is called stratum. So this is basically the terminology which we use in stratified random sampling. So stratum 1, stratum 2, stratum K, and each stratum, so for example, stratum 1 has N1 units, stratum 2 has N2 units, stratum K has Nk units. Okay, so since it has N1 units, so this Y11, Y1, N1, so these are the basically units here. So we are basically giving them numbers in order to identify them. So it is basically coming from which of these stratum. So the y11 is telling us that it is the first value in the stratum 1. Y1 and N1 is saying that it is the N1th unit in the first stratum. Okay. Similarly, others are defined, and here for each of here, this is the stratum, this is the stratum, this is the stratum. Each stratum, the mean is like a y1 bar, capital Y2 bar, and yk bar. Now, how to do the sampling? So from each stratum, a sample is collected. Now these samples can be collected by using any of the technique depending upon your requirement. Now, since we have only studied about the simple random sampling, so we are basically considering here that let this sample be collected using the simple random sampling. Okay, whether it can be SRSWR or SRSWR, because we have only studied that only that in the previous classes. Okay, so this sample 1 is collected. So from capital N1, small n1 units are collected. From capital N2 units, small n2 units are collected, and capital Nk units, small nk units are collected. Now we have also named it here that y11, y1n1, and here also we have the sample means. Okay, so now we have population means. We don't have only one population mean. So that is also a population mean. So that will be the bigger mean. And we have the, or I can say we have the stratum means. So for example, for stratum 1, I can have a mean. For stratum 2, I can have a mean. For stratum k, I can have a mean. And I may combine these all means to get the whole population mean. Okay, so basically, from the n units, I have divided this into n1 units and n2 and nk units. In this way we have divided. So basically summation of ni is capital N. Now from this n1 we have collected a sample of small n1, collected a sample of small n2, collected a sample of small nk. So basically what is the sample size? So small n, so we have collected a sample of size summation ni I going from 1 to k. So this is basically the sample size, and this is capital N is the population size. Okay. Further, what about the now the population mean? So now what will be the population mean? So that will, so basically population mean will be, if I say the whole population, so this is y11 plus y12 plus till y1n1. So this is the for the stratum 1, then y21 plus till plus y2n2 plus yk1 till yknk. So this is the whole population. Okay, now whole population, and what is the total number of the units in the population? N. So if I divide it by capital N, so this will now be the population mean. And now I also know that this sum is what? So this sum is here. I can from here I can say that this sum is this sum is n1 y1 bar. Okay, so it is 1 upon n n1 y1 bar, and similarly others, and this is nk yk bar. Fine, and we can write it in the summation form summation ni yi bar, where I going from 1 to k, and similarly this is written. Fine, so this is the basically the population mean. So we are basically summing all the units in the form of these stratums, units from these stratums. Okay, now here this we are just giving the terminology wi to this ni minus n, ni divided by n. So this is wi. So this is summation wi yi bar. Now this is the population mean. Now if I want to estimate the population mean, so one of the estimator of the population mean is this y bar st, which is given by all the quantities are same, only in place of capital yi bar we have the small yi bar, which is the sample means of different sample means which are collected from different stratums. Okay, so this is basically the estimator, and in fact this is an unbiased estimator for y bar, capital Y bar. Okay, so this is the unbiased estimator. So if I want to estimate the population mean for the stratified random sampling, that I will just use this stratified mean, okay, to find out the estimate of the population mean. Okay, so this is kind of a weighted average. Fine, where weights are given according to the number of elements present in a particular stratum. in such a way. Okay. So this is about the this unbiased estimator of the population mean. Now what about the variance of this y bar st? So if I consider y bar st under SRSWR, then variance will be this wi square ni minus ni upon ni into si square, where si square is nothing. So if I consider this sample, so sorry, this one, so capital Si square will be 1 upon capital N1 minus 1 summation these quantities minus the mean average whole square. Okay, in that way. So basically, if I say here, not this, so this Si square is nothing but the if from each stratum, so S1 square is the for the stratum 1. Okay, the variance for the stratum 1. So that is basically I'm taking all the entries and I'm subtracting the mean for that, and I'm squaring, summing, and dividing by ni minus 1. And it is performed for each stratum. And if I found those Si squares for each of these stratum, and then I will just find out this expression. So that is variance of y bar st. Okay, what can be the estimator? So for that, in place of capital Si square, we'll get small si square, because under SRSWR, small si square is a unbiased estimator of capital Si square. Okay, so hence this estimator will be unbiased estimator for this variance of y bar st. Similarly, if I use the SRSWR, then we have different expression for the variance of yi bar. So this is basically ni minus 1 upon ni into ni si square, and also which is equals to wi square sigma I square divided by ni. So here this sigma I square is nothing. In place of ni minus 1, we are just using ni, capital Ni, and then we'll get the sigma I square. Okay, now for SRSWR, this Si square is unbiased estimator for sigma I square. So in place of sigma I square, we'll just use Si square in order to find the estimate of this estimator for this. So this is again an unbiased estimator for this variance of y bar st under SRSWR. So we have different expressions for both the cases. Okay, so this is about how to find out the variance of the stratified mean, which is basically an estimator of population mean under stratified random sampling. Okay, now what about the confidence interval? So we have two cases for this. So if I'm doing a stratified random sampling and I'm assuming that the samples are large. So for example, this small n1, this is small n1, this is small n2, and the small nk, these are large enough, they are not very small. Then what I can do, so then in those scenarios, I can use this confidence interval where we are using y bar st minus z alpha by 2 square root of the estimator of variance of y bar st. Okay, here I'm using the standard normal distribution. So basically z alpha by 2 I'm using. But if some of the NIs are small, so if some of the NIs are really small, then what I can do, I'll just approximate this by t distribution. But now here the degrees of freedom for the t distribution will not be n minus 1, which we have considered before. So this here the degrees of freedom is coming through an approximation, which is proved in the theoretical concepts of this statistics. So where the expression for the degrees of freedom is this one. So that is summation gi si square I going from 1 to k whole square divided by summation gi si to the power 4 divided by ni1 minus 1. So here gi is nothing but capital Ni minus ni divided by small ni. So this basically we got. So if I know that I know the whole things about it, I know the what is the basically the population, the number of units in the population, number of units in different stratums, number of units in different samples. Then from those, if I know the variances also, or Si square, the standard deviation, then I can find out these expressions and I can find out the degrees of freedom. Now those degrees of freedom will be used here in order to calculate T alpha by 2 comma nu. Okay, so this way the confidence interval is calculated. Okay, for stratified random sampling. So this was about the topics, about the I've just given the recap of what has been discussed. So two things has been discussed. Some of the concepts about how to find out the if the data is qualitative, then how to convert it into quantitative and find out the the estimates of the population proportion and the variance of those estimates or the estimators. Okay, under different sampling techniques. And apart from this, we have started a new topic called stratified random sampling. So I've explained the how this stratified random sampling, the procedure for stratified random sampling, what are the notation, and how can we find out the population, how can we estimate the population mean, and what are the variances of those estimators. Okay, apart from that, how can we find out a confidence interval for the population mean. Okay, so for that we consider two scenarios: when the sample size is large, and when there is some small sample sizes, then we just consider this approximation thing. Okay, so we will discuss some of the questions on these topics, so then it will become more clear. So just let me know if there is some doubt. So kindly let me know if there is some doubt. Otherwise, we'll start the practice questions. Okay, so if there is no doubt, then we'll move towards the practice questions. Okay, so this is the first question. So which basically says that a sample of 20 students is drawn. So n is equals to 20 is drawn. Okay, by SRSWR with replacement from population of size 200. Okay, now I want to and the what are the what is recorded in that sample. So gender is recorded and stored in a vector gender. So basically this is a vector, sample vector. So this gender, in this gender vector, these all the data is there. Okay, so since it is a kind of a big data, not that big, but I have not included that data in the slides, and I have just given that data in the R script. So let me show that. So this is the data. Okay, so this is the data gender. So let me run it. So now this data is here with us. So basically this is the data. Now what it says, so just give me a minute. Okay, so in the first question, it is asking that using R, estimate the population proportion of males. Now, the population proportion of males I want to estimate. So in the population, I will give 1 to males and I will give 0 to females, because I want the population proportion of males. So the class from which the persons which are males, I want them to give as 1, and the persons who are females, I want to give them 0. So for that, what I will do, I will just create another vector x. Okay, so which I'll write gender is equals to male. So this basically give me a logical vector. So what it will give me, it will give me true wherever there is male, and it will give me false whenever there is female. So let me run it x. So I'll now get a logical vector. So let us see. So this is the logical vector now. Okay, now if I do s dot numeric x, so it will give me 1 at the places where there is true and 0 at the places where there is false. So I will just write s dot numeric x. So see here y. So now we got this quantitative data. So now from the qualitative, I've converted this into quantitative, like the data in the form of 1010. Now we know Now this is the estimate the population proportion. So in the first one, so sample proportion. Sample proportion. What is the sample proportion? Small p. What is it? It is basically 1 upon n summation of yi, I going from 1 to n. So which is basically nothing but the sample mean. So here yi is the this indicator. So yi is 1 when it belongs to class C and yi is 0 whenever it belongs to C star. So this 1 upon n summation of yi, so this is nothing but the sample mean, and which is basically the sample proportion. So this is an unbiased estimator of population proportion, capital P. Okay, now we have constructed this vector, or I can say the sample yi 0101 type of. So in order to calculate 1 upon n summation yi, we'll just use the command. So use the command. Which command we will be using? We'll just use mean of y, where y is that vector which consists of all the yi's. Okay, so if I use this mean of yi, so this will be the estimate of population proportion. So I run it. So I've just printed that an estimate of population proportion of males is 0.65. Okay. So it is the estimate for the proportion of males. So which basically is showing that the males are more comparatively females in the population. Okay. So this is about the first question. Now estimate the variance and standard error of the estimator. Now for the second one. So now this is the estimator, small y bar or small p, I can say. So what is the variance of, so this is basically the sample proportion. So it is, or I'm only writing small p. So this is the variance of small p. Okay, so what is the variance of small p? So that is equals to, so variance of small p is what? So that is variance of small y bar, which we have discussed before also, because this p small p is nothing but the sample mean. So now what is it? So now what was the method? SRS with replacement. Okay, so for with replacement we have this quantity as capital N minus 1 divided by capital N small n into, so I want estimator of it. So if I want estimator of it, so it will be, for with replacement it will be, it will not be this, because so that is, or I can say not the estimate. First I'll write this expression only. So if I write this n minus 1 divided by capital N small n capital S square, it was like this, and this was nothing but the sigma square by small n. Okay, and now if I want to write an estimate, so it is estimate of y bar variance of, and this is nothing but small s square by n, since small s square is unwise estimator of sigma square under, so this is important, SRSWR. Okay, so that will be our this, and the standard error for P will be SQRT of variance of P. Okay, so if I do this in R here, so first of all, in this, I want the small n, so which is the length of the sample. So I've just restored that in small n, and variance of p hat, which is this quantity. Okay, so I've just named it as p hat. Okay, the estimator of the population proportion. That's why it is written like this. So that will be variance of y by small n. So small s square is calculated by this command variance of y. So it will be variance of y by small n. So what will be the variance of p hat? So variance of p hat is nothing but the estimator of population proportion, or I can say it is the sample proportion. So this is 0.0119. So what we got? So this is 0.0119. Okay. And what is the estimate for the standard error? So what is the standard error? So it is 0.1094. Okay. So this is about this thing. Now further, estimate the population total of male students. Okay, so for male students, what will be the population total? So population total will be what? For the male student, there is 1, and for the female student, there is 2. So population total will be, capital N into capital Y bar. Okay, and if I want to estimate it, so it will be capital N into small y bar. So this is the sample mean. So in the R, what I can say, I can just assign this T hat to this capital N star, okay, mean of y. Or if I assign this value in something, then I can do that also. So here, see, I have this. So here I have printed this variance and mean. Sorry, variance and the standard error here. So this is 0.0119, 0.109. And since capital N is 200, if I want to find out the estimate of total population of the males, then it is 1. It is coming out to be 130. So it is basically saying, so this is coming out to be 130. So it is basically saying, so that an estimate says, so estimate says that there are 130 males in the population of 200 persons. Okay, so there are approximately 130. So this is an estimate. This cannot be the exact quantity, but it is saying us, okay, there may be 130 males. So basically in 200, so basically we can say there are more number of males compared to females in a population, which we have, okay, based upon the sample. I'm saying this. Okay, so this is about the first question. Now, is there any doubt? Any doubt regarding this question? Okay, so then we'll move for the next question. So now here a sample of 15 adults is selected. So n is equals to 15 is selected by the technique SRS WOR from a population of size 300. Okay, now smoking status is stored in vector smoke. So there is a vector smoke, okay, where the smoking status is stored. So whether the person is a smoker or a non-smoker. So that thing is stored, and this is a sample of 15 observations. So here I have stored that in R. So this is the smoke data vector. So let me store it in R and show you that what is the vector smoke. So this is the vector. So this is the data we have. Okay. Now I want to estimate again the population proportion. So here, since the random sampling is SRSWOR, then also the population proportion is not affected by it. So only the sample proportion is the, again for like a previous case, sample proportion P, which is equals to 1 upon n summation of yi going from 1 to small n, which is nothing but the sample mean y bar, is unbiased estimator of capital P, which is the population proportion. And if I want to estimate it, okay, if I want to estimate it, then I'll just use the command. First of all, I will construct the quantitative random variable. So since I want the proportion of the smokers, so I'll give 1 to the smokers and 0 to the non-smokers. So for that, I will just use this x, such that x is equal to smoke is equals to smoker. So it will give true on the smokers and false on the non-smokers. Further, by using s dot numeric, it will give 0 on non-smoker and 1 on smoker. Okay, so this is random variable x and y, qualitative and quantitative, and now we have this quantitative random variable y. Okay, now I want to find out the population proportion, so that will be nothing but the sample mean. So that is p hat. Okay, So what it is coming out to be? So it is coming out to be 0.6. Okay. So this is coming out to be 0.6. So which is basically showing us that more than half of the population is smoker. Okay. Now further estimate the variance and standard error of the estimator. Okay. Variance of again now y bar. Now under SRS WOR without replacement, we have this to be equals to n minus n divided by nn into s square. Now this can be estimated by, so this is n minus n upon nn small s square. So we'll just code it in R, n minus n divided by n star n and the whole thing multiplied by s square, or I can say VAR of y. This s square can be calculated using this. Okay, and the standard error will be nothing but the SQRT of VAR hat y bar. Okay, so this I have done here in this. So here we have just printed the first of all the estimate of population proportion of smokers, I can say. Is this. Okay, 0.6. Further, I want to find out the variance and the standard error. So by using the same formula, I can just find out this thing. So here the estimate for the variance is 0.0162. So this is coming out to be 0.0162, and the standard error is the square root of this thing, so 0.127. 0.127. Okay. Further estimate the population total. So again, the population total is, so what is the population total here? TP is again, so this is capital N into y bar. Okay, and this TP, and TP hat is capital N into small y bar. Okay, and what is the variance of this TP hat? So that will be capital N square variance of y bar. And the technique is here SRSWR, that is without replacement. So it is n square into, so variance of y bar without replacement I'm saying. So it is n minus n upon n into capital S square. So estimator for this is, we want to estimate the population total. Okay, fine. We do not want the variance, estimate of variance. We only want, here it came here. Yeah, so we only want not the variance, we only want TP hat. So that is capital N into y bar. So in the R we can just find the T to be capital N star mean of y. So this is the thing, N star into P hat. I've stored this mean into P hat, that's why I'm using this. So it is T hat to be 180. So it is estimated that there are 180 smokers out of 300, and it is an estimate only. Okay, it is not the exact thing, it is an estimate, not exact. Okay, whenever we are taking the sampling from the simple random sampling, it is an estimate based upon the sample. Based upon the sample, we are just predicting about the population, that in the population of 300 people, there are, maybe there are 180 smokers, or we can just say that there are more number of smokers than compared to the non-smokers. Fine. So I hope this is clear. We have discussed two questions where one of them we considered the simple random sampling with replacement and another we considered without replacement. Now let us consider this third question. So here we have a sample of 30 households is selected by simple random sampling without replacement from the population of 600. So 30 households is selected by simple random sampling without replacement from this to be 600. Okay. Now, internet access is recorded as yes or no. So, whether those in the population, it is just asked that whether you have internet access or not, and answers are recorded in yes and no, and the sample is stored in this vector internet. Okay, so this is a sample vector. So we have this vector. So I have just stored all the entries in this vector internet. This is sample. Okay. So if I should show you, so this is the vector of the samples. Okay, this is of size, this is of length 30. Okay, now I want to again find out the population proportion so that we basically know. So first of all, we'll just make it as a quantitative random variable or quantitative sample. We have it as a qualitative. So basically, I want that estimate the population proportion of households with internet access. So where there is yes, I want to give them one, give that entry to be 1, and where there is no, I want to give that entry to be 0. So I'll just write this conditional statement x such that x is given like internet is equals to yes, so it will give me a logical vector. So where there is yes, it will give me true, and where there is a no, it will give me false. Okay, then I'll just use the as dot numeric thing here. So it will give me the vector y, which is quantitative data vector. Basically the entries are quantitative here, where there is 1 where there is yes, and 0 where there is no. Fine. Now again, I want to find out uh, the estimate of population proportion. So estimate of capital P is equals to small p, so which is basically small y bar, so which is basically mean of y. So where we just do this in R like p hat, and this is coming out to be 0.733. Okay, so it is coming out to be 0.733. Okay, so basically by this we can say that in the population, so this is the population proportion of the persons which are having internet access, so which is basically more than 0.5. So there are more than half of the population is having an internet access. We can basically infer this thing from this study or from this sample at least. This may not be true, but by the sample it is basically, it is showing, the sample is showing that there are more number of people which are having internet access in the population of these 600 households. Okay, as compared to the persons which are not having internet access. Fine. Now again, I want to estimate the standard error. So for that, I want to estimate the first of all the variance. So the estimate of the variance of this P. So this basically was there with us before also. So under SRS without replacement. So this is n minus n upon n into small s square. So which can be like, it is the variance of the y, and these things we know. So standard error will be SQRT of variance of this p hat. So this in R we have done this n minus n upon n variance of y, and the standard error is given here. So estimate of the variance and the standard error both are given. So this is 0.0064. So this is coming out to be 0.0064, and the standard error is coming out to be 0.080. Fine. In the next, construct 90% confidence interval for the population proportion. So 90% confidence interval for capital P. So first of all, what is alpha? So 1 minus alpha is 0.90. which implies alpha is 0.10, which implies alpha by 2 is 0.05. Okay, so what is Z alpha by 2? So Z alpha by 2 can be find out using the command qnorm. And what is 1 minus alpha by 2? What is 1 minus alpha by 2? So that is 0.95. So which is nothing but q norm 0.95. Okay, so Z alpha we can find out by this. So what is basically the confidence interval for it? So the confidence interval will be the small p or the y bar we already calculated. So this was this quantity 0.733. Okay, p minus Z alpha by 2 square root of variance of p, this one, comma p plus Z alpha by 2 square root of variance of p. Fine. So this is basically the standard error which we have calculated. This p also we have calculated. This Z alpha by 2 can be calculated using this command qnorm. Okay. So what is basically it is coming. So p is what? So it is 0.733. So 0.733 minus. What is Z alpha by 2? So here is this q norm 0.95. So it is 1.6448. Okay, so it is 1.64 approximately. And what it is, the standard error, so it came out to be the 0.080. So it is here, it is 0.080, comma this 0.733 plus 1.64 into 0.08. So this will be the confidence interval. So if I evaluate here, so in the whole thing, so I have just, so the confidence interval is this one. So 0.6016, 0.6016, comma 0.8649. 0.8649. Okay, so this is basically the confidence interval for the population proportion. So is this fine? So through R we are not calculating manually. We are just giving the code and we are just finding out the confidence interval. So what is the confidence interval? We are just giving the formulas which we have obtained from the theoretical analysis. Okay. So I hope this is clear. Fine. So we'll move for the next question then. So here the question is, let the estimator of population total under stratified random sampling. Now we came to stratified random sampling. So let the estimator of population total under stratified random sampling be this. So this is the quantity T star hat. So this is an estimator of population total, which we do not know whether it is an unbiased estimator or not unbiased estimator. So first it is asked that is this estimator unbiased? Okay, and if it is not unbiased, what will be the bias for it? Okay, so first let me tell you, first of all, I'll write the expression for the population total. So in the stratified random sampling, we have different stratums. Okay, and from each stratum, we have different number of units in each stratum, and the total number of units we have capital and total number of units. So basically in the stratum 1, we have y11, y12 till y1 n1. So we have n1 units here. Okay, in the stratum 2, we have y21, y22 till y2 n1 n2 units. So here we have n2 units. Similarly, we have kth stratum and we have yk1, yk2 till yknk, which have nk number of units. Okay. So what will be the first of all the population total? Total population total will be, so TP will be what? It is the sum of all the units. So it is y11 till plus y1n1. plus y21 till y2n2 plus y plus dash till then yk1 plus dash till yknk. So it is the population total. Okay, so what will be, first of all, it is asked about the population total. So TP is this. Now I know that this quantity y11 till yn. So if I find out, we already know that we know that y1 bar. So it is for the first stratum. So this is y1 bar is equals to 1 upon n1 summation y1j, where j is going from 1 to n1. Okay, so which implies summation y1j, j going from 1 to n1 is equals to n1 y1 bar. I've just taken it there. Okay, similarly, so this is true for each of these stratum. Similarly, summation j value 1 to n2 yij is equals to n2 y2 bar, and summation j is equals to 1 till nk yij is equals to, okay, so not yij, it is y2j, it is ykj. Okay, and it is equals to nk yk bar. So here in this quantity I can see that this is n1 y1 bar, this is n2 y2 bar, and this is nk yk bar. So what TP can be written as? So the population total can be written as summation. So what it was? n1 y1 bar, n1, so not this, so I'll write it as n1 y1 bar plus n2 y2 bar plus nk yk bar. Fine. So TP is nothing but summation I going from 1 to k ni yi bar. So this is basically the expression for population total. Okay. Now what is asked in the question, that is this estimator of population total? Okay. So an estimator T star is an unbiased estimator of TP, which is the population total, if expected value of T star is equals to TP. Okay, it is equals to TP, then T star will be an unbiased estimator of TP. If not, okay, then bias is equals to expected value of T star minus TP. So this is the bias. So if it is an unbiased estimator, then bias will be 0 because they both will be equal. And if they're not 0, then this is the basically the bias. Okay, so let me take a blank page. Okay, so let us see that what is the expected value of T star. Whatever estimator we have given, so it is T hat star. So expected value of T hat star is nothing but expected value of, what is the expression, summation I going from 1 to k small ni y bar. Summation I going from 1 to k small ni yi bar. Yi bar is the sample mean for each of the, from the each stratum we are taking a sample, and the average of that sample is the small yi bar. So this is nothing but expectation will go inside I is equals to 1 to k ni expectation of yi bar. Now since we have drawn the sample using the simple random sampling, whatever it is, with replacement and without replacement, we are taking just the expectation. So there is no difference. So whatever the simple random sampling we have taken, expectation of small yi bar will be the capital yi bar. So it is summation I going from 1 to k small ni capital yi bar. Okay. And what was TP? What was TP? It is capital Ni yi bar. So it was capital Ni yi bar. So are they equal? No, they are not equal. So which implies TP is not an unbiased estimator of, or not TP. So T hat star is not an unbiased estimator of TP. Okay. Further in the question, it is asked that what is the bias. So bias is equals to expected value of T hat star minus TP. So which is what? So expected value of T hat star is summation small I, summation I going from 1 to k Ni yi bar. Okay, and minus TP is summation I going from 1 to k capital Ni yi bar. Okay, so bias will be what? Bias will be summation I going from 1 to k small ni minus capital Ni into yi bar. So this is the bias. Okay, is this question fine? Is there any doubt in this question? Okay, so if there is no doubt, then I'll move for the next question. So here in the question it is asked, which of the following stratified estimators is always unbiased estimator for the population mean under simple random sampling without replacement within strata? Okay, so these are the stratified estimators. So these are basically estimators and we are considering them as estimators for population mean. Okay, so for the population mean, first of all, I want to write what is the population expression for the population mean. So first of all, let us write an expression for the population mean under the stratified random sampling. So under stratified random sampling, okay, population mean. So what is the total number of units in the population? It is capital N. Okay. So the population total, if I write population total divided by the total number of units, so that will be basically be the population mean. Okay, if we sum all the entries or all the units and divided by the total number of units, then it will basically the mean of those units. So I'll just write, so the population mean, that is capital Y bar, is nothing but TP divided by capital N. Okay, and what was TP? We have previously calculated TP to be summation capital Ni yi bar. Okay, so it is summation capital Ni yi bar, I going from 1 to k, and it is nothing but 1 by n here. So now this is basically the population mean. Okay, so that is y bar is equals to summation I going from 1 to k Ni minus Ni divided by n, yi bar is the population mean. Now we'll talk about the estimators. If I talk about the first one, so is it an unbiased estimator or not? We'll just check it. So if I talk about A, so the estimator is 1 upon n, 1 upon capital N, summation small ni, I going from 1 to 1 to k. Okay, yi bar. Okay, so this is an estimator of, we are considering it is an estimate of y bar. Now we'll check that whether it is an unbiased estimator or not. So whether expectation of this estimator is what? So expectation of this estimator is yi bar I going from 1 to k. So this is nothing but summation I going from 1 to k ni by capital N expected value of yi bar. Now this again we were considering about the simple random sampling. So this expectation of small yi bar will be capital yi bar. So it is summation I going from 1 to k small ni by capital Ni yi bar. And is it equals to this quantity capital yi bar, which is the capital Y bar, which is the population mean? So which is not equals to capital Y bar. Okay, what it implies? So this implies, so the expression in A is not an unbiased estimator of capital Y bar. It is not an unbiased estimator, but what is the bias? Basically, this quantity minus y bar. Okay, so this quantity will be this quantity minus y bar. So it is small ni by capital N, here capital Ni by capital N. So this will be, so bias will be what? And bias is what? Bias is equals to summation I going from 1 to k small ni minus capital Ni by N to yi bar. Okay, because here we have in the denominator we have n common, and the small ni capital Ni in subtraction, and yi bar we can take common. So this is the bias. Okay, now we talk about the second one, B part. The expression is small ni by capital small n. Okay, the summation small ni by small n I going from 1 to k yi bar. Okay, if I take expectation of this quantity, so this quantity will be summation I going from 1 to k small ni by n expected value of yi bar. So which is capital yi bar. So this is equals to summation I going from 1 to k ni by n yi bar, which is again not equals to y bar, because there it was capital Ni and here it is capital N. Okay, so this is again a not an unbiased estimator. So I'll take a page here. Okay, so this is again, so again the expression in B is not an unbiased estimator of y bar. And what is the bias for it? So this minus the expression of y bar. So what was there? There was capital Ni and capital N here. So it is the bias. So the bias is summation. So bias is summation I going from 1 to k small ni by n minus capital Ni by capital N into yi bar. This is the bias. Now we consider the third part. So what it is? So it is, here we have capital Ni by capital N into yi bar. So if we consider, so summation of capital Ni by N yi bar, I going from 1 to k. If I take expectation of this quantity, we can see here directly that from I equals to 1 to k, it is Ni by N. Expectation of yi bar will be capital yi bar, which is nothing but the population mean. So this implies that this is an unbiased estimator of population mean y bar. Fine. So here the bias will be for this. So bias will be 0 for C. Now if we consider D, 1 upon n summation Ni capital Ni. So 1 upon n summation capital Ni yi bar to k. If I take expectation here, then similarly we can see that it is nothing but this Ni by small n capital yi bar, which is not equals to y bar. So implies that this is an biased estimator. Okay, this is an biased estimator. And what is the bias for it? Bias is what? 1 upon n summation. Okay, so it is, so this expression, this one, summation I going from 1 to k ni by n minus capital Ni by capital N yi bar. So this is the bias. Okay. So we have basically it checked that whether the estimator is biased or not. I think it is not written here. So this was about this question. So this was about the whether an estimator of a population mean is an basically particular estimator is an unbiased estimator or not. So we only got an estimator where there is capital Ni and capital N. That estimator is basically the unbiased estimator for the population mean. Okay. So now after this theoretical question, we'll move towards a kind of a numerical question. Okay, for the stratified random sampling. So just first consider this data or the values of different quantities. So here the population is divided into three strata. So k is equals to 3 here. Okay, so this is basically the k. Now, a stratified random sample is drawn by simple random sampling without replacement within each stratum. Okay, so basically the sample is drawn using the technique simple random sampling without replacement. Okay. Now, what is basically the size of the particular stratum? So first stratum is of size 500, second stratum is of size 300, third stratum is of size 200. From the first stratum, a sample of size 80 is taken. From the second stratum, a sample of size 60 is taken. Or from the third stratum, sample of size 40 is taken. Okay, and also the means are given. Mean sample means for the samples which is taken from the first stratum is 52. The second sample mean for the second stratum is 60. The sample mean for the third is 48. And also the SIE squares, which is basically the sample variance, is also given. So it is 100 for the first one, 144 for the second one, and 81 for the third one. So these quantity we have with us. Now I want to estimate the population mean first. So first of all, I want to estimate the population mean. So basically we have, as discussed, population mean can be estimated by using the stratified mean. Okay, which is y bar st. Okay, so which is what? Which is summation I going from 1 to n. First of all, this is the stratified mean. I is equals to 1 to. So first of all, let me write the population mean. Okay, first me write the population mean. What basically is the population mean? So population mean is capital Y bar, so which we have already discussed. So it is summation I going from 1 to n, not n, k. I going from 1 to k, capital Ni by small n, not capital N, into a yi bar. Okay, now this quantity is, can be estimated by an unbiased estimator, which is given as the stratified mean, y bar st. How it is given? It is summation I going from 1 to k, capital Ni by n as it is, and in place of capital YR, we have small yi bar. Okay. So for here we have y1 bar, y2 bar, y3 bar. Capital Ni's also we have. These are the capital Ni's and these are the small ni's. So let us write this. So capital N1 is equals to small n1 is equals to, and y1 bar is equals to n2 is equals to small n2 is equals to and y2 bar. So let us see, this was 500, 300, 200. So it is 500, 300, 200. This is 80, 60, 40. So 80, 60, 40. And here it is 52, 60, 48. 52, 60, 48. So y bar st is nothing but this divided by this into this. Okay. So this is 500 by 80 into 52 plus 300 by 60. Oh, not this. Capital N. So what is capital N basically? So capital N is summation of capital Ni's. So which is 500 plus 300 plus 200. So this is 1000. So 500 divided by 1000, 300 divided by 1000 into this thing 60 plus 200 divided by 1000 into 48. Okay, this one. So this is nothing but it got cancelled, it got cancelled, it got cancelled. So it is 0.5 into 52 plus 0.3 into 60 plus 0.2 into 48. Now if I simplify this, so I've done this calculation. So we simplify it, so it is nothing but 26 here, okay, plus 18 here plus 9.6 here. Okay, so let me write it in the next slide. So it is equals to 26 plus 18. So 26 plus 18 plus. So it was 96. Sorry, 9.6. So yeah, so it is nothing but 53.6. So this thing I have also included in R. So this was basically y bar st. So that this is an estimate. So this is an estimate of population mean. Okay, so let me show this in R also. So this is this one. So here what I have done, I have just taken this vector 500, 300 and 200 for the uh, different number of units for different stratums, and small ni's to be the number of units in each of the samples or from the each stratum. Okay, y bar is the values of this y1 bar, y2 bar, and y3 bar. So I have just stored them as a vector, and so these are these quantities. So if I run it, so I got these quantities, and this capital N is the sum of ni's. Okay, so which basically is the sum of all these items. So this is the total number of units in the population. Okay, this S2 I will talk about later. Small wi is capital Ni by n, so this is nothing but this quantity, this quantity is capital Ni by n. Okay, so we basically want the that is n1 by n is multiplied by y1 bar, and then we have one value, and we want to sum it by n2 by n into y2 bar plus n3 by n into y3 bar. So we basically do it by using this command y. So wi is calculated by Ni by n. So we'll basically do sum of wi into y bar. So what it will do, it will just take w1 into y1 bar. So for example, at the first place, so let me show this to you in R. So y bar will be what? So y bar will be this 52, 60, 48. So which we have found out here also. So it is 50, so it is so not found out, so we have just stored 52, 60, and 48. Here I want this, and this quantity is capital Ni by small ni. Sorry, capital Ni by capital N. So that is this Wi quantity. So what it is? So if I show this to you in R, so this is capital Wi. So which is this 0 0.5, 0 0.3, 0 0.2. So I just want to multiply this 0 0.5 into 52 plus 0 0.3 into 60, 0 0.2 into 48. So if I multiply them only, then I will get a vector where multiplication is between the entries on the same position. Then if I sum it, then the this y bar st will come, because I want this kind of expression only, not this one. Because I want to multiply, then I want to sum all of them. So basically, through this multiplication, we have created a vector. Through a multiplication, we have created a vector, and then we will sum it over. Then we'll get y bar st. So here in the similar way, this y bar st is calculated. This is sum of yi star. So for example, if I only run yi star y bar, wi star y bar, so it is nothing but 26, 18, and 9.6. The same thing which we have also came across. So this is 26, 18, and 9.6, and then we will just sum this here, this sum. Okay, so then it will give me y bar st, and which is nothing but the estimate for the population mean. So let me print this. So it is the estimation of the population mean, which is coming out to be 53.6, and here also we got this. Fine. Now further, here the first question is done. Now the second one is to construct 95% confidence interval for the population mean. So 95% confidence interval for y bar. Now since the sample sizes were large enough, so it is sample size is 80, 60, 40, it is not that small. So we'll use approximation for z alpha y2. So we'll use the same formula. So the confidence interval will be what? Y bar st minus z alpha y2 square root of variance of y bar st estimate. Okay, and the same thing, y bar st plus z alpha y2 square root of variance of y bar st, the estimate. Okay, this we know already. This is 53.6, which is stored in y bar. Okay, and this z alpha y2 is what? So alpha is 0.05, since this is 1 minus alpha 0.95, and alpha is 0.05. So alpha y2 will be 0.95. Okay, and not 0.95, 0.025. Okay, and z alpha y2 will be can be generated or can be calculated using the command q norm 0.975. So let us calculate that first. So this q norm thing, q norm 0.975, if I find out here, actually I have written it directly, but let us find out. So it is 1.959, so I can write it as 1.96. So it is 1.96. Okay, now variance of y bar st is remaining. So variance of y bar st. So which is nothing but variance of what was y bar st. So y bar st was summation I going from 1 to k capital Ni by capital N into y bar st was yi bar. So this was our y bar st. Okay, now this is equals to nothing but summation I going from 1 to k capital Ni by capital N whole square variance of yi bar. Okay, now the simple random sampling without replacement we have considered here. So this now summation I going from 1 to k capital Ni by N whole square, and this is capital Ni minus small ni upon capital Ni into Si square. Okay, now since this is not known, so we will just estimate it. So variance hat of y bar st under simple random sampling without replacement, small si square is unbiased estimator of capital Si square. So this can be written as small, this the whole thing is as it is, and this is small si square. This can be calculated by using the command var thing. Okay, so here in this question we have calculated this quantity var of st as we want wi square. So here this quantity is wi square. This quantity is, if I write it as 1 minus, sorry, 1 upon no, 1 minus small ni by capital Ni and si square by small ni. So similar way I have written it in this way. Okay, and this will give us the variance of st, which is this quantity, this quantity. So what it is coming by using the R code, so you can just go through it, and it is only the formulation for this function only. Okay, this one. Okay, so it is variance and standard error will be the square root of it. So it is what it is coming, the standard error is coming out to be 0.7071. So it is coming out to be, so let me run it again. 0.7071, the standard error. Okay, so this quantity where it is, so now here only I will write, so square root of variance of y bar st estimate is coming out to be 0.7071. Yeah. Okay, so the confidence interval now will be, so confidence interval will be what? So we had y bar st to be 53.6. So it is 53.6 minus z alpha y2 came out to be 1.96, I guess. So it was, yeah, 1.96, and this is coming out to be sorry, 7071. Okay, this comma 53.6 plus 1.96 multiplied by 0.7071, and this is coming out to be, so I have just given the command here. So what it is coming out to be, it is it is showing some error actually. Okay, so one bracket is less here, that's why it is showing the error. Okay, now it is fine. So let me run it again. There was some error in it. Yeah. So it is coming out to be 52.213, comma 54.986. Okay, so this was about how to find out the confidence interval for the population mean whenever we are considering the simple random, the stratified random sampling. Okay, and the samples are taken from each of the stratum using the technique of simple random sampling without a placement. Further, we will move towards if the sample sizes are small, then we have how to calculate the degree of freedom for the student distribution by that formula through using R code. Okay, so we'll move for that. So let us consider this thing. This so a population is divided into three strata. Again, we have three strata population, the division of the population into three strata, and we have three stratum with us. Okay, so each of the stratum, one of them is of size 200, another is of 150, and third is of again 150 size. Sample sizes are 6, 5, and 4, which are very small, and the sample observations are given. Okay, now here the mean and the sample variances is not given, or the sample observations are given. So for each sample observation, we'll calculate the mean here for the y1 bar. This is y2 bar. This is y3 bar. Small y1 bar, y2 bar, and y3 bar, and small s1 square, small s2 square, and small st square for all of them. Okay, then we'll go towards the finding out all these things about the population, the estimate, how to estimate the population mean. First of all, again we have only that estimator, that is y bar st, so which is basically nothing but summation I going from 1 to k, which is 3 here, capital Ni by capital N into yi bar. So for that I need to find out first the yi bar. So what I'll do, I'll just take a vector in R to be this observations, another vector x2 in R which is of this observation, another vector x3 of R of this observation. So these are basically three samples coming from these three stratums. Okay, so here I have constructed these three vectors x1, x2, and x3. Okay, now if I want to find out the y bar, so yi bar, so y1 bar, y2 bar, y3 bar. So if I take mean of this x1, I will get y1 bar. Mean of x2, I will get y2 bar, and mean of x3, I'll get y3 bar. So this is mean of x1, mean of x2, mean of x3. I've stored this in again in a data vector y bar. So let us see. So what is basically the means are coming? Let us see. So it is 40, 46, 42.5. So if I see, so here, so the what are the y bars are coming, yi bars are coming. So here it is 40, it is coming, it is 46 and 42.5. 46 and 42.5. Okay, so which is basically a summing them and divided by 6, summing them divided by 5, summing them divided by 4. So this is coming. Okay, now further similarly, if we'll find out the sample variances. So SI squares. So if I find out SI squares for them, so what is that? VAR of this thing, it will give me the SI squares. VAR of this thing, it will again give me as a S2 square. VAR of this thing, it will give me the S3 square. Then I will store this in again in the vector. So here for S2, so S2 is that vector. So let us see what they are coming. So it is 2, 2.5, and 1.67, I can say. So it is 2, 2.5, 1.67. So this is done. So this we will be using further in calculating the other things. So here we want Ni by N yi bar. So again I have this vector with me, and I have this vector with me, and these all quantities I have Ni and N. So again I will just do it in R and find out. So capital Ni is here 200. So 200, and the capital N is what? We will be summing this over. So this is 200 plus 300. This is 500 here. So this is 200 by 500 into, so what was the y1 bar? It is 40 plus 150 by 500. So it is 500 multiplied by 46 plus 150 by 500 multiplied by 42.5, I think. Yeah. Fine. So this will basically be the estimate. So let us see here. So it is coming out to, so Ni, small ni's and capital Ni's are again stored in a vector because we want them. to find out the things. So now what will be the estimate for the population mean? So it will be the, so basically we'll calculate the wi vector. So wi will be capital Ni by, so capital Ni by capital N, so capital N1 by capital N, capital N2 by capital N, capital N3 by capital N. So this is stored in this wi vector. So if here we'll see here, so what is wi here? Capital Wi. So this is 0 0.4, 0 0.3, 0 0.3, which is nothing but here this is 0 0.4, this is 0 0.3, this is 0 0.4, sorry 0 0.3 again, and this 40, 46, 42.5 is stored in this vector 40, 46, 42.5. We have this vector, we have this vector, we just multiply them and we'll sum it over, then we'll get this expression. Okay, so same thing we have done it in this y bar st, and that will be the estimate for the population mean. So here we found out that the estimate of population mean is 42.55. So it is 42.55. Fine, so this was simple. This was just like before we did. Now I want to construct the confidence interval. 95% confidence interval. So the alpha is here 0.05. So alpha by 2 will be 0.025. So T alpha by 2 with new degrees of freedom. This is be calculated QT 0.975. This is 1 minus alpha by 2 comma nu. I need to calculate nu for that. Okay. So for that I need to calculate nu. Okay. What is the expression for the nu? We know before we have discussed that how to calculate nu. This is the expression for it. Summation GISI square whole square. Okay. So it is summation GISI square a whole square divided by summation, I think GISI to the power 4 divided by Ni minus 1 a whole square, where it is, I don't know. It is GI square Si to the power 4 Ni minus 1 GI square Si to the power 4. It is GI square Si to the power 4 summation I going from 1 to k, I going from 1 to k, and what GI is here? GI is nothing but Ni into Ni minus Ni upon Ni. Let me see it. Ni into Ni minus Ni upon Ni. Fine. So this is GI. So first of all, let us code for GI. We know capital Ni, we know small ni. So it is, so for I is equals to 1, it will be G1. I is equals to 2, it is G2, and I is equals to 3, it is G3. So we'll construct a vector G1 which consists of G1, G2, and G3. Okay, so here it is constructed GI, which is nothing but Ni minus Ni divided by Ni. So this is GI. So Ni, I already know that capital Ni is this 200, 150, 150. So this will do the mathematical thing, and this will find out this vector GI. So this is coming out to be 6466. So the G1 is 6466.66. Okay, G2 is coming out to be 4350, and G3 is coming out to be 5475. Now using this GI and SI square, so SI square we already have S1 square, S2 square, S3 square with us. Okay, what were those values? So those values were 2, 2.5 and 1.67. Okay, we already have them. In a vector it is stored 2, 2.5, 1.67. It is also stored in a vector. Okay, we want to multiply this. I want GI SI square, so I will multiply them. Then I will sum them. So I want to sum GI asterisk SI square I want to first of all multiply them, then I will sum them, okay, then I will take the whole square. So I will take the whole square of it in the numerator part. So this is basically I'm telling you in the perspective of R. So this is a vector Gi, this is a vector Si, and I'm just multiplying these two so that each entry will get multiplied to the elements in the same position, and I will sum it to get this expression, and I will square it to a the square, so I will do to the power 2. Okay, now this whole thing is divided by what? It is divided by this thing. So here what I want to sum, what? I want to sum Gi square, okay, multiplied by, here it is Si square. So there the data, it is stored in the form of S2. So let us write it as S2, okay, because this data is stored in the vector S2. So it is S2 to the power 2 square. So it will become Si to the power 4 divided by Ni minus 1. So it is like sum this divided by this in Ni, and these whole both the things are divided here, and this will be the new. Okay, so in the R you can see, so this is nothing but sum of Gi into S2 and whole square we are doing divided by sum of Gi square star S2 square divided by Ni minus 1, and we are summing. So sum is outside all this quantity. So this is Gi square multiplied by S2 square divided by Ni minus 1, and then we are summing it over. And then we are dividing both the quantities, then it is new. Okay, so if I find out, see, the value of nu is coming out to be 11.94. So here it is coming out to be 11.94. Fine. So what will be T alpha by 2 comma 11.94? So this is basically QT 0.975 comma 11.94. Okay, so this is basically here. So df is equals to nu, I have written, nu is already 11.94. So here this quantity will be 2.179. So it is 2.179. Okay, and also we have to find out what? Variance of y bar st, this estimator. So this estimator, again we have this simple random sampling without replacement. So previously we also had this expression, this y bar st. In a similar way we will find out the y bar st for this one. So this way this y bar st is here, this summation of wi square 1 minus ni by ni s2 divided by ni. This is in a similar way previously we have done. So it is, so the standard error, so the variance will be, this variance of st will be variance of st will be 0.1317. So 0.1317, and the standard error, that is the square root, is 0.3629. 3629. Fine. So what will be the confidence interval then? Y bar st was what? Y bar st was 42.55. So it is 42.55 minus this quantity 2.179 multiplied by this quantity 0.3629, okay, comma 42.55 plus this quantity. Okay, so then what we will get, the variances, if I find out. So it is 41.75 comma 43.34. So this way we will do if the sample size, this sample sizes are small, then we'll just approximate the degrees of freedom using the formula. So we'll just code it in R and directly get the result for the degrees of freedom. Then we'll get this quantity, find out the variance, estimate of the variance of y bar st, and find out the confidence interval. Okay, so this was the last question for today. If anyone have some doubt, then you may ask. And apart from this, I want to inform you that the recording for today's session will be uploaded on YouTube. And the PowerPoint presentations and the R script I will be uploading on the Google Drive. And the deadline for the assignment is 4th of March. And your next section, this next live session for this week 7 will be on 9th of March from 6 to 8 p.m. as usual. So if someone have some doubt regarding anything, then you may ask. Otherwise, we'll just end this meeting. Okay. Okay, so if there are no doubts, then we'll end this session. I hope that you people try to try to watch the content which is already shared in the on the NPTEL for the next week, and we'll discuss the concept and the practice examples for those that week also in the next session. Okay. Okay, fine. So thank you for your patience. Thank you for joining the class. We'll end the meeting now. You may leave.